In a quest to understand the vast and mysterious universe, science has long mastered the powerful tool of logic. But even when using the most rigorous methods and the most advanced technologies, paradoxes inevitably arise, contradictions that challenge our understanding of the world. One such paradox is the dark sky at night. How is it possible that we're surrounded by an infinite number of shining stars, and yet the sky remains dark? The other is the nature of dark matter, an elusive substance that escapes the grasp of even the most advanced instruments. And what about the inevitability of oblivion? The solar system, along with our planet and ourselves, may eventually disappear into oblivion, forever lost in the vastness of time and space. These paradoxes are not just philosophical ruminations. They have real implications for our understanding of the universe. They force us to reconsider our assumptions and question the things we think we're sure of. They encourage us to go beyond our current understanding and delve deeper into the mysteries of the cosmos. And in the end, faced with these paradoxes, we can gain new understanding and move forward in our comprehension of the universe. The Horizon Problem. The Horizon Paradox, also known as the Horizon Problem, is a paradox arising from the observations that the temperature of the cosmic microwave background radiation, or CMB, is practically uniform throughout space, despite the fact that regions of the universe separated by vast distances have not had enough time to reach thermal equilibrium. The root cause of the Horizon Problem is that the CMB is a remnant of the time the universe was in a hot and dense state known as the Big Bang. The CMB is the almost perfect black-body radiation, characterized by the uniform temperature of approximately 2.7 Kelvin in all directions. However, if the universe continued to expand, in about 13.8 billion years, certain regions of the universe separated by such vast distances would not have time to reach thermal equilibrium and therefore be of the same temperature. This paradox suggests that the temperature of the CMB does not have to be the same throughout the universe. The Horizon Problem has baffled cosmologists for decades and prompted a number of proposed solutions. One solution is the theory of cosmic inflation, which states that the universe underwent a rapid expansion in the early stages of its formation. This expansion would have smoothed out any initial fluctuations in temperature, making the temperature of the CMB about the same throughout the universe. Inflation models also explain the homogeneity and isotropy of the universe, two more major observational mysteries in cosmology. Another possible answer is the concept of causality. Causality is a fundamental principle in the sciences. It's the idea that every occurrence, action, or event is preceded by a cause that determines its effect. The idea is that the early universe was in equilibrium and was much denser and hotter. Photons of relic radiation in this state of the universe were in casual contact. That meant they could interact with each other and achieve thermal equilibrium. The third solution is the concept of cosmic variance. The gist of this idea is that the universe is much larger than we can observe, and temperature fluctuations are simply statistical deviations from the average temperature of the universe. In general, the Horizon Paradox is a complex and multidimensional problem that has not yet been fully resolved. Each of the proposed solutions has its own strengths and weaknesses, and a true resolution of the paradox may require a combination of these ideas or even an entirely new theory. Olbers Paradox. Olbers Paradox, also known as the redshift paradox, is a mystery that's puzzled astronomers for centuries, named after the pioneering German astronomer Heinrich Olbers. This paradox arises from the contradiction between the presumably infinite number of stars in the universe and the darkness of the night sky. The gist of the paradox lies in the fact that if the universe were truly infinite and eternal, and the stars were evenly distributed throughout the endless bounds of outer space, then in any direction we looked, we would see a star. The light from these stars, however distant, would eventually reach our planet. Therefore, the night sky should be illuminated with the same intensity as the surface of the sun. However, despite this logical reasoning, the night sky remains dark, presenting a perplexing enigma for scientists and stargazers alike. Several possible solutions have been put forward to explain this mystery. One solution is that the universe is not uniform and isotropic, meaning that the stars are not evenly distributed throughout space. This could be due to the presence of large-scale structures such as galaxy clusters and voids that would create dark patches in the night sky. In addition, light from the more distant stars could be absorbed by intergalactic dust, making the night sky appear darker. This theory is supported by observations of major redshifts in distant quasars. Another possible solution lies in the expansion of the universe. The farther back we look, the further away the light sources would be from us. When we look back into the past, the universe becomes denser, more hotter and brighter. As a result, the light from distant stars is shifted to the red end of the spectrum and therefore become too faint to be seen. We can't say for sure whether our universe is infinite, but according to the Big Bang Theory, we know one thing for sure: our universe has a beginning. Additionally, the assumption that the universe is a finite would mean that the light from distant stars does not reach us simply because our universe is constantly expanding. Because of this, the wavelength of the light from distant stars is greatly stretched, and it eventually reaches Earth in the infrared range. It would also mean that the light from distant stars has either not yet managed to reach us or the stars have already died out. On the other hand, if we assume that our universe is infinite, then it's quite natural that at some point, due to the constant expansion of the universe, stars and matter would begin to acquire a speed that exceeds the speed of light. This would make it impossible for light to reach Earth. The enigma of the Olbers Paradox remains one of the most intriguing mysteries in cosmology, and its solution requires a deeper understanding of the nature and structure of our universe. The Flatness Problem. The Flatness Problem is a paradox that arises from the observation that the universe is almost perfectly flat, despite the fact that the density of its matter is far from sufficient to maintain such a state, which begs the question, why is the universe flat? And what do we mean when we classify it as such? The flatness of the universe means that space-time is not curved and the amount of matter and energy is just right for the universe to be flat. However, the density of matter and gravitational energy in the universe are much lower than necessary, which should cause it to either expand too quickly or collapse. And this, of course, makes us wonder, how does the universe maintain its flat shape? In a nutshell, that's the essential principle of the flatness problem, a mystery that continues to haunt some of the greatest minds in the field. There are several possible solutions to the flatness paradox. One potential solution is the elusive concept of dark energy. It is believed this mysterious form of energy contributes to the acceleration of the expansion of the universe. Dark energy is believed to contribute 68% of the total energy in the present-day observable universe. It has negative pressure and acts as a repulsive force, counteracting the gravitational force of matter and causing the universe to expand at an accelerated rate. This acceleration would help to flatten the universe. Another solution is the concept of inflation. According to the theory of inflation, the universe underwent a rapid expansion in the early stages of its formation. As space expands, the geometry of space becomes flatter. To help you understand, imagine a balloon. As it fills with air and inflates, its surface becomes smoother and flatter. This type of expansion would smooth out any initial density changes, making the universe nearly flat. The third solution is the multiverse theory, which suggests that our universe is just one of many. According to this theory, there are a large number of universes, and based on this, the likelihood that one of them will be flat is much higher than if there was only one universe. The Monopole Paradox. The Monopole Paradox is yet another example of an unyielding mystery of the universe. This is a paradox that comes from the observation that there are no observable magnetic monopoles, despite the fact that their existence is predicted by several theories of particle physics and should be present in the universe. Magnetic monopoles are hypothetical particles with a single magnetic pole, while all known magnets have a north and south pole. The existence of these hypothetical particles has been predicted in theories such as the Grand Unified Theory, a Grand Unified Theory or GUT, and quantum gravity theories. However, despite great efforts and extensive research, no magnetic monopoles have been found. Nonetheless, despite their elusive nature, there are many theories attempting to explain their apparent absence. One possible explanation for the absence of magnetic monopoles is their instability. That causes them to decay into other particles, making them undetectable in the modern universe. Another theory claims that magnetic monopoles were created during a supersymmetry transition in the early universe, but they're now too rare for us to be able to observe them. The idea is that in the early universe, the symmetry of the laws of physics was different than it is now, and these symmetries were broken during a phase transition, similar to how water changes from a liquid to a solid when it freezes. During this phase transition, magnetic monopoles should have appeared as a result of breaking symmetry. However, as the universe has expanded and cooled, these monopoles have diluted and are now too rare to be observed. The search for these hypothetical particles continues, as does the scientific work with a goal to unravel the monopole paradox and deepen our understanding of the universe. The Entropy Paradox. The entropy paradox is a paradox that arises from the observation that the universe is ordered and structured, despite the fact that the second law of thermodynamics states that entropy, or in other words, disorder, must increase over time. But what does entropy actually mean? We usually talk about it as if it were a measure of disorder, a quantitative representation of the randomness and chaos that exist within a system. A broken egg on the floor has more entropy than an intact egg on the countertop. A spoonful of cold cream and a cup of hot coffee have less entropy than the combination of both stirred together. A chaotic pile of clothing has a higher entropy than a neat set of drawers where all the clothes are folded and organized. According to the second law of thermodynamics, the total entropy of an isolated system will always increase over time. The law implies that the universe should become less ordered as time goes by. However, the very structure of the universe contradicts this idea. We observe that the universe is highly ordered and structured. It contains galaxies, stars, planets, and even life forms. There are several theories that offer possible solutions to this paradox. Each of these solutions offers a different perspective on how the order and structure observed in our universe can be reconciled with the second law of thermodynamics. One solution is the concept of entropy as an arrow of time. The arrow of time is the idea that time has a direction moving from the past and into the future. This concept suggests that while entropy would increase in a closed system, it doesn't necessarily happen in an open system like the universe. At the same time, it can still freely exchange matter and energy with the environment, which makes the second law of thermodynamics inapplicable. Another solution, known as the emergence theory, suggests that at the macroscopic level, structures and order can emerge spontaneously, even though entropy increases at the microscopic level. This idea suggests that while entropy increases on a small scale, it can lead to order on a larger scale. Finally, some scientists believe that the answer to the entropy paradox may be provided by the expansion of the universe. The expansion of the universe increases the volume of the observable universe, which in turn reduces the entropy of the system. This means that even though entropy increases locally, the overall entropy of the universe can remain constant or even decrease due to the universe expanding. The last two theories are similar in concept and could potentially complement each other in solving the entropy paradox. The expansion theory offers a solution to the paradox by decreasing the total entropy of the system, while the emergence theory offers a solution by explaining how structures and order can spontaneously emerge despite an increase in entropy. The information paradox. The information paradox, also called the black hole information paradox or Hawking's paradox, is a problem in theoretical physics. It suggests that black holes absorb information, thereby irretrievably destroying it. But what do we mean by information? Information in the context of this paradox refers to quantum parameters that describe the state of a physical system. These parameters contain all the information needed to fully define the state of the system. They play a central role in the principles of quantum mechanics. Quantum mechanics believes that the entirety of information in the universe is conserved, meaning that it can neither be created nor destroyed. Now, let's go back to how this paradox arises. It happens because of the contradiction between the two most established theories in physics: quantum mechanics and the general theory of relativity. Up to a certain point, the laws remain intact and have no effect on each other. But this only happens before the Hawking radiation comes into play. The information paradox was first brought to the forefront of scientific discourse by Stephen Hawking in the 1970s. He proposed that black holes emit thermal radiation that lacks any information about the matter that has entered the black hole. This led to the idea that information is forever lost when it enters a black hole, and the fundamental laws of physics are not deterministic. The information paradox has been the subject of much discussion and research in the decades following its discovery. One proposed solution is black hole complementarity, an idea that suggests that the information sucked into a black hole is not actually lost, but is instead encoded on the black hole horizon in a way that's consistent with both quantum mechanics and the general theory of relativity. To represent the complementarity of black holes, it's important to consider the same physical process from two different points of view. From the point of view of an observer outside the black hole, the information entering it seems to be lost forever, as it's pulled toward the singularity at its center. However, from the point of view of an observer from within a black hole, this information is encoded on the horizon in a way that's consistent with quantum mechanics. The key to understanding the complementarity of black holes is to recognize that a black hole's horizon is the boundary between two different regions of space-time. On one side of the horizon, the laws of general relativity operate, and on the other, the law of quantum mechanics. Information falling into a black hole is encoded on the horizon in a way that is consistent with both sets of laws, providing a possible solution to the information paradox. Another proposed solution is the firewall paradox, which states that information is not lost, but instead stored by a firewall of high-energy particles surrounding the black hole. Despite all the aforementioned theories, the information paradox remains one of the most difficult and important unsolved mysteries in theoretical physics. It is integral for our understanding of the nature of black holes, the principles of quantum mechanics and general relativity, and most importantly, the ultimate fate of the universe. Dark matter and dark energy paradox. The dark matter-dark energy paradox, also known as Bentley's paradox, is a problem in physics that arises from a discrepancy between the observed behavior of galaxies and other large-scale structures of the universe and the predictions of the standard model of the universe. A key piece of evidence for the existence of dark matter and dark energy is the observed gravitational effects of these mysterious substances. The standard model of cosmology based on general relativity predicts that the observed gravitational effects of the rotation curves of galaxies and the large-scale structures of galaxy clusters must be much weaker than they actually are. The discrepancy is known as the gravitational paradox, and it's led scientists to suggest the existence of dark matter and dark energy to compensate for those gravitational effects. Dark matter is estimated to make up about 27% of the universe, and it's speculated to exist based on its gravitational effect on visible matter. It doesn't interact with light or other forms of electromagnetic radiation, which makes it difficult to detect directly. Scientists have proposed various candidates for the role of dark matter, including WIMPs, WIMPs, weakly interacting massive particles, and axions. However, despite decades of research, neither of them have been detected with any degree of certainty. Scientists also believe that dark energy makes up about 68% of the observable universe and is responsible for the acceleration of the expansion of the universe. Its existence is confirmed based on observations, but the nature of dark energy is not entirely clear. The most popular explanation for dark energy is the cosmological constant, proposed by Einstein, which is a form of energy evenly distributed throughout the universe. However, this explanation raises some issues such as the cosmological constant problem and the coincidence problem. These problems stem from the fact that the observed value of cosmological constant is much lower than the theoretical predictions, as well as the fact that it has the same order of magnitude as the density of dark matter. It's also worth mentioning that the current standard model of cosmology, the lambda CDM model, which uses the concept of dark matter and dark energy, corresponds with a wide range of observational data and is considered the most successful model of the universe to date. Bentley's paradox refers to the fact that even though dark matter and dark energy make up such a significant part of the universe, their exact nature remains a mystery. Many theories have been put forward to explain their properties, but none have been conclusively proven to be accurate. The discovery of new particles or new phenomena that could help explain the nature of dark matter and dark energy would be a major breakthrough in our understanding of the universe. The paradoxes that arise when exploring the universe and its governing laws are not obstacles, but rather opportunities for growth and development. They represent a puzzle that pushes the boundaries of our understanding and requires new theories and explanations, lighting a spark for further research in the field of cosmology. Each resolution of a paradox is a step towards not only in solving a particular problem, but also towards our overall understanding of the intricacies of our universe.